So in this video we're going to do the kinematic model, which involves integrating the remote control so we get 3 axes of translation and 3 axes of rotation, and we need to do that before we can make it walk. So the first part of the kinematic model is going to be solving this leg length from the hip to the ankle and trying to move this ankle up and down in a perfectly straight line. So you'll notice the foot is directly below the shoulder joint at the moment. What we need to do is modify both the shoulder and the knee joint as we give it data or give it a length for this distance here. So on paper that looks like a triangle, which I've drawn in red here, and we're going to give the input is going to be this length here, which we're going to call Z, and that is the height of the robot from the ground. Now you'll notice the triangle doesn't quite converge at the actual point where the foot is touching the ground. Depending on the angle of the shin here, that's going to be a different place. So I've just assumed that it's in the middle for now. There'll be some error. Now cunningly, this distance here and this distance here are both 125 millimeters. They're both the same, and that was part of the design because I knew I had to solve this model. And that means all the angles in the triangle, not only will they add up to 180 degrees as they do with any triangle, but it means that this angle and this angle will be the same. So as long as we can solve one of the angles in the triangle, then we can easily work out the others because 2 of them are the same, and we can do 180 degrees minus the other 2, and that gives us the one we haven't solved. And all we need, of course, is to solve one angle, so we're going to use this first example here, which involves a bit of Pythagoras theorem by the look of it, and finally some trigonometry. And here it is in code, so I've essentially gone through each stage, and I've got a different variable for each stage so I can check it. Eventually we do an inverse cosine, which gives us the angle. Now this angle is in radians, which is what programming languages typically use, so eventually we'll have to do a conversion into degrees. So if we convert degrees to radians with this Google page, we'll find 1 radian is roughly 57 and a bit degrees, 2 is 114, and all these numbers look a bit weird until we get to a very familiar looking number of pi, 3.1415927, and that's 180 degrees. So you'll remember me saying that we could get 180 and take away the 2 other angles to find the other one, but of course it's not 180 degrees, it's 180 in radians, which is pi. So we're doing pi minus the other angle times 2, which are the 2 angles the same, and that then gives us both angles for the knee and the shoulder. So then for each leg, I've taken off the offset, so the knee is already at 90 degrees and the shoulder's already at 45, and then I've multiplied that by a scaling factor, and that is to get the microseconds value to actually drive the servo to the right angle. So I've now mapped the twist of the right hand stick to that leg length input. So now as I turn that stick, we should find those legs getting longer and shorter, and it's calculating the trigonometry about 100 times a second every time that loop goes round, so it should always remain with the foot perfectly under the shoulder. Now we do have a situation where the knee servo has to move further than the hip servo, and both of these servos have motion filters on at the moment. I'm actually filtering the servos individually rather than the actual Z demand, and that means depending on how fast I move this, obviously we exceed the maximum speed of the motor, and one motor can get there faster than the other one, so that means it doesn't necessarily move in a straight line, and to do that we need to interpolate through every position on the way and drive it slower than the maximum speed of the motor. But actually, having checked this with a ruler and a protractor, it looks like my angles are correct, and it looks like my leg moves to the right length. And of course my robot is compliant anyway, so any minor errors get taken out in the natural flex in that compliancy. But of course the result is that the robot does go up and down, and that's the first axis of our kinematic model.